I'm going to talk about uniform circular motion, and we have to discuss the conditions we need in order to have uniform circular motion, which includes having a constant velocity and a circular path. Some of the vocabulary we need for this unit is the radius, which is from the center of the circle to the outside of the circle. So that's R right there, the radius. And the diameter is twice R. So if you are given the diameter and you need the radius, it is going to be 1/2 the diameter is equal to the radius. That's just a reminder. The other thing is circumference, and that is just the path we travel as we go around the circle. And we have that equation in the reference table, and it is equal to 2 pi r. First, we need to look at circular speed in a circular path. So we want to know what the speed is as we go around a circle. And we get that just from the average velocity equation, v equals d over t. But we need to consider what this distance actually is. As we said on the last slide, as we go around, the total distance is going to be equal to 2 pi r, and then it's still the amount of time it takes to travel that distance. So it's the circumference divided by the time in order to get the velocity in one revolution. Now, if we are going to go around that circle more than once, we need to consider the number of revolutions we have gone in order to get our velocity. So we can really write it as the number of revolutions times 2 pi r divided by time. And often this right here is just one revolution, and this term will go away. But we do need to make sure that we are paying attention to the problem and to what we're looking at, and include it if we need to. So we have a sample problem that says the combined mass of a race car and its driver is 600 kilograms. Traveling at constant speed, the car completes one lap around a circular track of radius 160 meters in 36 seconds. What is the speed of the car? So we can say that we're looking for the speed of the car, and we can say it's v equals 2 pi r over t. We know that we have a time of 36 seconds, and we know that the radius is 160 meters, and the number of revolutions is just one. And so from there we can find this speed. So it's just v equals 2 pi times 160 meters divided by 36 seconds, and that gives us 27.9 meters per second. So we also need to talk about frequency and period of something in circular motion. Frequency is the number of revolutions or cycles something happens each second. Its symbol is F, and its units are 1 over second, which is equal to hertz. F is equal to the number of cycles per second, which is also the number of revolutions per second. The period is the time it takes for one complete revolution around the circle. Its symbol is a capital T, and its units are seconds, and it's, again, the time for one cycle. And the period and frequency are related. The period is equal to 1 over the frequency, and the frequency is equal to 1 over period. So if you have one, you can find the other. So we've talked about a few of the conditions and things necessary to talk about things that are in a circular path. But is it really accelerating if the speed is constant? Well, if we have something going around a circle, the direction is constantly changing if it's at a constant speed. So velocity is the change in speed. And if there's a change in direction, then there's going to be a change in velocity. So, yes, if there is a change in velocity, there's an acceleration. So again, if there's a change in velocity, then there's a change in acceleration. So that's what centripetal acceleration is that change in velocity as it goes around the circle. So let's talk about the direction of the centripetal acceleration for just a minute. As we go around the circle, we have many different directions that this velocity is going, and we can choose one. So this is our initial velocity. It's going to go, if we let go of it right here, pretend this was on a string from the center, if we let go of it right here, it would fly off tangent to this circle in a straight line, just like you saw in the marble lab. It wants to continue in the direction it's traveling right here. And then if we have our final velocity, because we're just picking 2 points on the circle, we can choose it right there. So acceleration, just what we've seen before, is the final velocity minus the initial velocity divided by time. Now this part right here we can actually do with a vector sum, and normally we say a vector sum would be VF plus VI, but we want a negative instead. So we would just say VF plus a negative VI. So to do that, we just flip VI. So we have a vector like this for VF. VI looks like this. And negative VI looks like that. So to add them, we just go tip to tail. So I'll change color so it's easier to see. So the VI looks like that. And then VF, if you go to the tip here, and then the tail of VF, and then this is the change in V. So this one, just to label everything, VI, VF. And if you put that on the circle, you can see that it looks like this. The change in V is here, like that. Negative VI is exactly opposite of this right here. And then the VF points like that. So you can see that this change in V is pointed toward the center of the circle. So the centripetal acceleration So the direction of the centripetal acceleration points toward the center of the circle. And that's true in all cases. And it's a pretty important point in universal circular motion. So just a quick note, you may have noticed that I said that I have been saying centripetal. You may have heard of the term centrifugal, and they are two separate words. Isaac Newton came up with the word, well, he actually came up with both words in 1687. The word centripetal means center seeking. It's derived from Latin, and it is talking about the force needed to make something move in a circle. And its equation is centripetal acceleration is equal to v squared divided by r, which you worked with a little bit with the gizmo yesterday. Centrifugal is pretty much a made-up force. Usually the term is used incorrectly in popular media. Normally when they are saying centrifugal, they mean centripetal. So we are just going to stick with the term centripetal force and acceleration. Okay. So I have a quick sample problem for you. It says a 2,000 kilogram car travels at a constant speed of 12 meters per second around a circular curve with a radius of 30 meters. What is the magnitude of the centripetal acceleration as it goes around the curve? So we can write our knowns. We have a mass of 2,000 kilograms. The speed is going to be 12 meters per second. The radius is 30 meters. And it's asking for the centripetal acceleration. So the equation, as I said just a minute ago, is centripetal acceleration is equal to v squared over r. So all we have to do is plug in our values. So v is 12 meters per second, and we square that, divided by r is 30 meters. If we plug that into our calculator, we get 4.8 meters per second squared, and that's all we needed. The next part of this sample problem says, as the car goes around the curve, the acceleration is pointed in which direction? So the car is going around the circle. We have our lovely car. The car is going like this, and the acceleration is going to be pointed toward the center of the circular curve. And the actual question said it was just a curve, so we can actually get rid of most of this circle and just talk about the curve. But the acceleration is still going toward the center of the curve. So that's how we would write it. Just say toward the center of the circular curve. So the next thing we need to talk about is centripetal force. It's not a special force, but it's caused by another force. So say you have something on a string and you spin it around in a circle. The tension in the string, here the tension force, or maybe the force of gravity if you're talking about the Earth going around the sun. This force, the force of gravity, or even the frictional force of a car going around a curve, because the the force of friction is what makes it possible for you to go around or even to drive at all. So the centripetal force going around a curve is actually a frictional force, though that's what causes all of these forces. So in a free body diagram, we wouldn't really say FC, we would name the forces instead according to what they are. You may see FC on like the Regents test or something, but they're just trying to make it clear as to what you're looking for in that multiple choice question. But just know that it's not actually it's not a separate force. Something else to consider, we already spoke about which direction the centripetal acceleration is in. If you look at the equation F equals ma, which you looked at in the gizmo yesterday, you can see that the force should be in the same direction as the acceleration. So this, the direction of the force is also toward the center. So in order to calculate the centripetal force, we have to realize that we have the F net centripetal is equal to mass times acceleration. The centripetal acceleration times the mass is equal to the net centripetal force, just like we have for any other F net problem. So that means that the centripetal force is going to be mass times the centripetal force, and centripetal force, we already have that equation. It's v squared divided by r, so we can just plug that in, and that's where that comes from. So then we can do some pretty simple calculations based on that. So we have a centripetal force sample problem. It says a 1,750 kilogram car travels at a constant speed of 15 meters per second around a horizontal circular track with a radius of 45 meters. The magnitude of the centripetal force acting on the car is what? So we can write our knowns and unknowns. We have a mass of 1750 kilograms. The radius is 45 meters, and the magnitude of the centripetal force is what we're looking for. And it says a speed of 15 meters per second. So the equation we're using is Fc equals mass times v squared divided by r. And so we can just plug values in. The mass is 1750 kilograms. The velocity is 15 meters per second, and we square it. R is 45 meters. We plug that into our calculator, and we get 8750, and the unit is newtons. Okay, so we have one more sample problem. It says a 500-gram toy car completes 10 laps around a circular Hot Wheels track in 1 minute 40 seconds. If the diameter of the track is 1 meter, find the car's centripetal acceleration, the centripetal force, the period, and frequency. So let's write our knowns and unknowns. So the mass is equal to 500 grams and 500 grams we have to put into kilograms, so everything is in SI units, so that is just 0.5 kilograms. The radius is equal to 1/2 of the diameter, so you have to pay attention. So 1 meter divided by 2 is just 0.5 meters. It says it completes 10 laps, which is revolutions, number of revolutions. And the time is 1 minute 40 seconds. And we have to change that to seconds. So it's just 60 seconds plus 40 seconds is 100 seconds. Okay? And so those are our knowns and unknowns. Oh, well, our knowns. Our unknowns, we're looking for the period, the frequency, the centripetal force, and the centripetal acceleration. So the first thing we need to figure out is the velocity of this car. The velocity is going to be just the distance over the time, and that's going to be 2 pi r divided by t. So it is the distance it's traveling, which is 10 revolutions, times the 2 pi times the radius, which is 0.5 meters, divided by the 100 seconds. And that gives us 0.314 meters per second. So we can add the 0.314 meters per second to our knowns and unknown list. Then we can use that velocity, that speed, in order to find the centripetal acceleration. That equation is just the centripetal acceleration is equal to v squared over r. And v squared is 0.314 meters per second, and we square that quantity, divided by r, which is 0.5 meters. And we get 0.197 meters per second squared. Then we can use that acceleration to find our centripetal force, which is mass times centripetal acceleration, and that's going to be the mass, which is 0.5 kilograms, times the 0.197 meters per second squared, and that is equal to 0.099 newtons. And we can add that to our knowns and unknown list again. And then the last thing we want to find is our period and our frequency. The period is just the time it takes in the number of revolutions. And the time was 100 seconds in 10 revolutions, so that was equal to 10 seconds. If you have 100 divided by 10, it's 10 seconds. And then frequency is 1 over the period, so it then becomes 1 divided by 10 seconds is equal to 0.1 hertz. And those are our final things we're looking for. T is equal to 10 seconds. F is equal to 0.1 hertz.